is the first step should pretty much always be creating an environment where you make sure that all of your libraries are installed. And actually, you can also share this environment with your colleagues and stuff, so that everyone has the same setup, and you make sure that your code runs. So we're gonna create Conda or a Mamba environment. For those who don't know, Mamba is just pretty much the same as Conda, but it's written in C, so it is faster and it's more lightweight on your storage. So I'm gonna create my Mamba environment. I have an MRI together, so I'm gonna call MRI together too. I'm gonna use Python 3.8 because why not? You can see the syntax is just like the Conda one. Well, I'm assuming everyone has Conda installed or Mamba installed. There you go. So it's creating the environment. I should have prepared some kind of playlist for whenever my terminals and stuff. Anyway, you can activate your environment. Just like this. Mamba activate, just like you would do with Conda. And now you can see I'm inside, like I was on the base environment before, now I'm the MRI Together 2 environment. Cool. So the second step would be to install TEDANA, which is the tool we're going to be using to denoise our multi-echo data. And it's as simple as pip installing it. So install TEDANA, enter. It shouldn't take too long.
So it's Python package the only dependency here for the pip install TEDANA?
Yeah. So TEDANA, once you install TEDANA, I will take care of any other dependencies. Actually, if I scroll up here, so you can see TEDANA will collect NIPABL, SciPy, scikit-learn,
NumPy and stuff.
Yeah. Matplotlib, NumPy, yeah.
Okay.
So that command should take care of everything. And if you're not installing on inside of an environment, it could be the case that you already have some of those installed. But that can be a little bit problematic, especially with Bokeh. We've had some issues with Bokeh versions, so if you want, I would recommend to use an environment if you want to use the data. Cool. So it seems like it's installed. So we can check that it is actually the case, and we're gonna see if we're on the latest version. So we can do TEDANA /dash version. I don't know why it keeps telling us there's a due credit error. Like it cannot find a module. We still haven't found out why, because it's not part of the package anymore, but it's still showing up. So don't worry if you see that. TEDANA will still work. It's taking a bit of time. Oh, there you go. So we're on version 0.0.12, which is the latest one. Cool. So yeah, no, it means that we can already use TEDANA. If you don't know what options we have, what arguments you can pass, you can do TEDANA-h to see the different inputs that you can use and their description. We have two required arguments that are the files, so the multi-echo data files and the echo times. And then we have a bunch of other optionals like the output directory, the mask, prefix, convention, and so on. Cool. I'm going to create a folder, and I suggest you do the same to store the data, because we're going to be downloading some data to play with. So, all right. Well, I actually have the. I did some testing, so I'm going to move into the folder. And this is going to be where we work. Now, we're going to be using a open dataset, just subject from it. So I would recommend that you use this link. I can paste it on the chat real quick. Data. There you go. And I'm also gonna open it in my browser. So we're gonna open the multi-echo folder here. I don't know if it's big enough. There you go. And we're gonna select one of the folders. The first one should be fine. And we're gonna download a zip. You've got it up here. So it says download starting. Good. So now we want to move the zip file that we just downloaded from downloads. So there you go. And we're gonna, since we're already in the folder, we're just gonna move it to the folder. And we're gonna unzip it. There you go. And just because I like my directories clean, I'll remove the file, zip file. Also, if the audience thinks I'm going too fast, please let me know in the comments. Good. So now we have the data. Let's see what we have actually inside of the folder. We're gonna move this a bit because there you go. So we've got the anatomicals, the functional, some logs, and the figures. This is because the data was pre-processed, minimally pre-processed with fMRI prep. And this is the folder structure that fMRI prep spits out. And since we're going to be denoising functional data, we are interested in the functional folder. So I'm going to have a quick look at what we have in there. There you go. So we've got some confounds that we could use to denoise the data as well. We've got 4 echoes that are partially pre-processed. Then we have some what looks like some transformation matrices or something, and we've got a mask. So for this tutorial, we're going to be using the 4 echoes, the mask, and the TSV file with the confounds later on. There you go. You also have this on the slides. So yeah, we are ready to go. We can start playing with TEDANA. Now, I know this looks like a big chunk of code. It's actually not that complex. So I'm gonna make this full screen again. What we want to do is we want to run TEDANA. By the way, you can run TEDANA from within a Python session as well, just so you know. Right now I'm outside of the functional data folder, because I would rather have the TEDANA folder outside just because it's cleaner, but now I'm thinking of it, it might be better if we put it inside the functional folder. So I'm going to move into the functional folder. Now we're going to call TEDANA. The D is for the data sets we want to input. So it's called sub 0457. Oh, I don't find it. I'm gonna copy and paste it. TEDANA. That's the first one. I'm gonna copy the second one, change it to echo 2. So we have to pass all 4 echoes in order. So from echo 1 to echo 4. And 4. Now the second required argument would be the echo time values. And these ones I know because I checked in another file. You can just copy them. So it's going to be 12, 28, 44, and 60 milliseconds. Then TEDANA automatically creates a mask of good, what we call good echo data. So we will mask out any voxels that do not have at least 3 echoes of good data. I personally like to use my own mask, just because sometimes this automatic masking can be too aggressive. So I'm going to use a mask that we downloaded from OpenEuro. So that's double dash mask. The name of the file is. Oh, I actually have it here. I'm gonna copy it. Cool. Now I'm gonna use a couple of other parameters as well. I'm gonna tell TEDANA that the output directory should be called TEDANA, just so we know. I'm gonna also choose among the different dimensionality reduction techniques. So TEDANA has a bunch of different ways of selecting the number of components that you should have. So I'm going to use the MDL option. Then I'm going to also tell TEDANA to use a prefix that is based on the file names that we had. So I just copy and pasted the brain mask file name, and I removed everything that was that looked like bits. So all the desk brain mask stuff. We're gonna keep the prefix of that for our output data. And then I'm gonna choose the fit type. So the TEDANA has 2 ways of fitting the multi-echo data. I'm gonna use the pure fit option. It's a little bit more computationally speaking, more expensive, let's say. But it should be slightly better than the other one. And then I'm gonna just use verbose because I want TEDANA to spit out all of the echoes, not just the optimally combined data. And that should be enough. But again, just having the data and the echo time should be enough for TEDANA to work. And if you're exploring how TEDANA works with your own data, maybe that's a good point. That's a good point to start with. Cool. I'm gonna write. Again, I will complain about due credit, and it's already telling us each of the steps that it's doing. So it has created the output directory. It's loading the input data, and now it's computing the T2SAR map that it will use to optimally combine the multi-echo data. And this might take a bit, not too long though. So I'm gonna try to explain what TEDANA is doing. So once the data is optimally combined, it will run a PCA step to reduce the dimensionality of the data and reduce the thermal noise. And once TEDANA removes the thermal noise and knows how many components it's gonna keep, it reconstructs those PCA components back into the matrix, and then it runs an ICA on that reconstructed data to find independent components. And these independent components are then classified as bold-like, so accept them, or they don't look like bold, and then TEDANA rejects them. And the idea is that you use this classification to denoise your data, which TEDANA will do automatically. Cool. So now it's just spitting out some metrics, and it's done. So we can now check the outputs. I'm gonna move this. Okay. So we can check the outputs. I'm gonna do ls TEDANA. It's a folder we just created. So if I just do ls, you'll see there's the TEDANA folder now. And ls TEDANA. So you can see that we get a bunch of files here. We get this many files because we use the verbose option. But the idea is that we get the S0 and T star maps. If you don't know what they are, I suggest you watch the talk that I gave about TEDANA on Tuesday. Then TEDANA also outputs some PCA and ICA metrics that are very useful for the classification step. It also outputs the optimally combined data and then each of the echoes separately. So you can choose whether you want to work with the optimally combined data or you want to use all of your echoes, denoise the echoes. Like I said, it will generate a mask of what it considers good data based on having at least 3 echoes of good data. And then it will also create a folder with component figures and a report, an HTML file with a report. Good. And like you saw, some of those files. So on the left, you can see a JSON file with the description of the different metrics that TEDANA uses and shares with as an output. And on the right, you can see the log that we actually saw live on the terminal. You also have it as a TSV file if you want to go back. Maybe there was an error or something didn't make sense on the analysis. You can always go back and have a look. Cool. But I have to say, as of today, the automatic classification of ICA components is not perfect on TEDANA. We are working on a new version that will let users come up with their own recipes. We think that will be much better than what we currently have. But I will mention that again at the end of the talk. Good. So why do I say that the classification is not perfect? If you were to open the metrics file, the TSV metrics file, which should be somewhere here. There you go. So here's the TEDANA metrics file. If we were to open this file on Excel or whatever, you would see there are some. So each row corresponds to an ICA component, and then you've got different metrics in the different columns. But the one I want you to look at is the classification one. So I have already colored the accepted ones to green, rejected ones to red, and then there are some ignored components that are blue that TEDANA will, by default, it will consider them as good just because it didn't know how to classify. So it will be more conservative, let's say. And it also says the rationale behind rejecting and ignoring components. Good. But honestly, I can actually open a Finder window here. If I open, I don't know if this is big enough actually. If I open the TEDANA window, you can see the TEDANA folder. You can see there's a figures folder with all of the components. You could go one by one and check if they make sense. That's how we used to do it until not long ago. But now we have a much better way of doing that. So we came up with RICA, which stands for Reports for ICA. And it is an easy and very fast way to both visualize components and classify them. So we're gonna open RICA. Here's the link. I'm gonna paste it on the chat. There you go. And I am going to open it myself. And hopefully it will work. Cool. So this is how RICA, how we get introduced to RICA. You can read the text if you want, but basically what we want to do is we want to select the folder, the TEDANA folder we just created. So that's, for me, it's together 2 functional TEDANA. And I choose to upload the entire TEDANA folder. It will ask me if I want to upload the files. I'm going to say yes. And it might take a few seconds to load. There you go. So what you see here on the info tab is some information that TEDANA outputs as a TXT file, as well as some of the references to work that TEDANA is based on, or different packages that TEDANA uses. We also have the carpets tab with the different carpet plots. So you've got the accepted, you've got so I don't know if you know what carpet plots are, but basically those are the intensities on all of your voxels across the whole brain. So they're good to see different artifacts like motion or breathing patterns that you might want to remove, or it could also be some background noise that you can remove. So you can see the carpet plot of the accepted components, of the noise data, of the rejected components, and you can see this carpet plot looks like, like you definitely don't want to have anything looking like this on your data. And also the optimally combined. And then there's the ICA tab, which is what we're interested in. And this is somehow a replica of the HTML report that TEDANA builds by default. But the biggest difference here is that RICA will allow you to change the classification that TEDANA came up with. And it will let you save this new manual classification so that you can rerun TEDANA with it. So I'm going to show you what you can do here. So there's the raw and kappa metrics. So you can have you can click on it, and it will show you the component figure that I really quickly went through just a few minutes ago. And so the idea is usually, and this is just usually or often the case, rejected components tend to be those with high raw values, and accepted components are usually those with high kappa values but low rho values. So if we were to draw a line around here, the green one should be around here, I would say, like the lower rhos but higher kappas. So you can see that in the rho kappa plot, but you can also see that in the kappa and rho ranks. Personally, how I usually approach this is I first have a look at those components that have the higher variance, that explain the higher variance in the data, just to understand what's going on here. So you can click on the plots. And then I usually go to the accepted components and then go through the whole thing with my arrow keys. So if I use the right arrow key, it will move, so left and right. I will do the whole loop and then see if I want to accept or ignore. Before I manually classify the blue ones, especially the ignored ones, I am also gonna show you that you can zoom in on the different scatter plots. So if I wanted to zoom in here, I could click and select the area. So then I can better understand the different values that the components have. But in any case, you can also see those values. So for instance, this one here is IC11, it's 15.34 for rho. You also have these values on the figure on the right. Yeah, and I think you can also use your trackpad to or your mouse to zoom in with a wheel, or scrolling. Cool. So I'm gonna manually classify the components just real quick. So how do I do it? I have a look at the map, see if it makes any sense, and same with the time series. If it looks like it could be bold or it's definitely an artifact. Usually, you know what an artifact is. Like for instance, here, this time series doesn't make any sense, or this one. So you want to remove this slow fluctuations from the data. And when in doubt, my suggestion would be to keep it as an accepted component, especially if the variance is low. So yeah, I'm gonna go through them, and if anything looks funny, I'll remove it. I'll reject it. But so far, it looks like TEDANA did quite a good job. We are also working on making. Well, I'm gonna say that later. So this one, for instance, it looks kind of funny, right? It could be the CSF, maybe it's kind of the time series is kind of high frequency-ish. That's probably related to some kind of pulsations. I'm gonna reject it. You can use A to accept, R to reject on your keyboard. So this one is clearly an artifact. You've got these stripy patterns here that you don't want to keep on your data for sure. I don't know why TEDANA didn't know how to reject that one by default. Same, this is a funny time series with big jumps that do not make much sense, that you would not expect to see on bold data, on bold responses, sorry. So I'm gonna reject that one. I'm gonna reject this one as well. Again, funny time series, and there's no specific frame activity pattern or regions coming out that make much sense. Same here, you can see some stripy pattern, and these huge drops in signal are kind of funny. I am also going to reject this one. This one's really high frequency, so I'm going to reject it. and this one too. And I think those should be all of the blue ones. I'm gonna quickly go through all the rejected ones to see if there's anything that should be accepted. Oh, look at this one. So this one's a clear artifact that when you look at this, you're like, yeah, of course, we're not gonna accept this. So you're always trying to find these kind of like patterns. This one looks like it could be veins. I'm gonna keep it as a reject. Again, those patterns here are very high frequencies, slow drift with stripes. Again, this one's really all funny what happens here at the end. Really high frequency, more stripes. The map here doesn't make much sense, and you can see kind of like a sinusoidal kind of like pattern. Yeah, it looks like TEDANA did a good job at rejecting, which is usually the case. Like the ones that TEDANA rejects are usually a clear reject, and it will not, it would rather ask you to reject manually the ones that TEDANA is not sure about.
So Eneko, what does ignored mean?
So ignored means that TEDANA didn't know if it should accept or reject.
So you have to make the choice in that case. Is that right?
You make the choice, or TEDANA automatically will treat them as accepted.
Okay.
Because it doesn't want it's playing the conservative game in that sense. Like,
so if you don't do anything, then it will be accepted.
Yes. Yeah. 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 All of these components look like they could be rejected. Cool. Imagine I made a mistake here and I wanted to like start over. You can use the reset button here. I'm not gonna do that because I don't remember which ones I rejected. But again, going back to the rho and kappa plot, you see that the green ones or the accepted ones kind of like are in this lower right area of the graph. That's usually the case. It could happen that there's another one with a higher rho that you want to accept, but yeah. And especially if you are expecting a component to follow your task and you know you want to keep it, make sure it's green, because it can happen that you've got some task-related component that TEDANA thinks is noise for whatever reason. So make sure maybe you want to remove it because it's a breathing, it's some breathing, related artifact that is related to your task or some motion related to the task, and you don't want to keep it. I mean, at the end of the day, you know your data and you know what you want to do with it. So yeah. So now you can save, click on save, and it will, well, it says download starting. So it will download a TSV file called manual classification. But before I close this window, you can click on about to, learn a little bit more about Rika and, open the GitHub page to see if you want to contribute or whatever. But you can also add or load new data. If you like have run TEDANA in parallel on a bunch of subjects and then you want to go through all of them, you can do that as well. Cool. I'm going to minimize this, and before I move on, if you do or want to learn and do web development, would like to contribute to Rika, please DM me, because right now it's a solo project that I'm working on. So I would really appreciate if someone else joins the project, because it's too big for me right now. Yeah, so like I was saying, Rika makes it very easy to run TEDANA with our manual classification. So we downloaded the manual classification TSV file. So we're gonna move it into the TEDANA folder. This is how I usually do it. Here it is, manual classification.tsv, and I want to move it into the TEDANA folder, just so I have this this file in it, and I can always go back and be like, okay, when I run TEDANA on this subject, this is how I manually classified the components. So I've just moved that, and now we can rerun TEDANA with this manual classification, and it will not run the PCA and ICA steps, but it will just take care of the denoising. So the command is going to be pretty much the same that we used before. There's going to be a few changes though. So the output directory, you can see here out there, I usually name it to TEDANA_manual. Just so I have, for each subject, I have the TEDANA and then the TEDANA manual folders. The prefix is going to be the same, verbose is going to be the same, but since we're rerunning TEDANA, we want to use some of the outputs that TEDANA already generated before. So we're going to give it the T2 star map. We're going to give it the ICA, what TEDANA calls a mixing matrix, so basically the ICA components. And then we're going to give it the C tab, so the component table, which is going to be the manual classification that we just did with Rika. Cool. So I'm going to make this bigger. And the command, as I say, is going to be pretty much the same. So I'm just using what I had before. I'm going to remove then the feed type and the CA step. And like I said, I'm going to be renaming the, well, not renaming, I'm going to be generating a new output folder called TEDANA manual. And that means we just have to add the T2 starter map. And that's in the TEDANA. What's the name of the thing? Subject. Prefix here. I'm gonna copy it. Prefix. Scanner, and then the T2 star map will be T2 star map. The mixing matrix. Oh, yeah. I was going to just paste it, but no. So the ICA components will be in the mixing matrix called scanner underscore desk ICA underscore mixin.tsv. And we're just missing the classification also. Manual classification.tsv. And I think I did not make any mistakes, so I'm gonna just hit enter, and we're gonna rerun TEDANA with a manual classification. So now you see it's not saying anything about running PCA or running ICA. It's just going straight to new metrics and the new denoising. Let's create a new images. Oh, I didn't know that FSL and SPM cannot deal with 64-bit integers. Okay, so it's done. And now I guess we're happy with the classification, and we have the noisy data. We can have a look and see what the denoise data looks like. So actually I could just make this bigger. So I'm gonna use carpet plots again, just to compare the optimally combined data with the denoised. So this is going to be the command that we're going to be writing inside of a Python session. So I'm going to open Python now. I'm actually, wait, I'm doing from within. Okay, so I'm going to move into the TEDANA manual folder. I'm going to start a new Python session. Good. And now I'm going to import matplotlib, and from Nylarm plotting, we're gonna import plot carpet. Okay. So we're gonna. This is not gonna work as I want, but it's good enough. Because as far as I know, the carpets cannot go in subplots, but if I show one of the plots now, then I cannot show the other one at the same time. So I'm just gonna create it as subplots. And so subplots, the one, yes. And in the first axis, I'm gonna plot carpet, the output file. And so it's gonna be desk, and the optimally combined is optcom underscore bold, and the mask is backend function in the functional folder. So prefix, and it's desk brain underscore mask. So, what did I? Desk dash brain mask. Isn't that the file name? Oh, because yeah, I know what the problem is. Yeah, sorry. It's not in the func folder, but like we're already in the func folder. That's the thing. I created the folder inside of the func folder. There you go. And now we're gonna do the same, but instead of giving it the optimally combined data, we're gonna give it the optimally combined data that has been denoised with a manual classification. So for that, I need to make it really small change here. Nice. Underscore bold. Yeah. And we're gonna plot this on the first axis here. And the mask is gonna be the same. Cool. And I'm just gonna show it. There you go. So yeah, like you can see here, it didn't do it the way I wanted it to do it, but it's good enough. So the one on the top is the optimally combined, and the one on the bottom is the optimally combined and has been denoised. And here you can see there's like stripy patterns, kind of like noisy pattern that has been removed with our manual classification. Yeah. So I'm gonna close this Python session, and I'm gonna go back to my slides. So yeah, like we just saw, the before and after would be that we no longer have this noisy pattern. But there are different ways of denoising that we can do, especially when we have some confounds from our analysis that we want to like remove along with the rejected components. So in order to do that, I'm gonna load some of the data on a new Python session. So I'm gonna be loading the data, mask, the confounds, and some of the metrics, because we're going to be using all of this in the 3 different denoising strategies that you can use. So I'm going to copy paste from here. Yes. I'm going to start a new session. And I think the way I have set it up might not work. Yeah, okay. I'm just gonna do it line by line then. Just to start a new session. So I'm gonna import from path, from os.path, import join basically to join different chunks of the path. And I'm going to import pandas because we have some TSV files. And so, yeah, the data file is going to be, it's going to be this one. So if you have the slides open, it's going to be much easier than what I'm doing right now. And then we have the mask file that's going to be desk brain underscore mask. This is going to be mask file. And then we have confounds file. And this is going to be desk dash confounds. Let's go to series.tsv. We also want to load the mixin file, so the ICA components, and then the metrics that say if a component is accepted or rejected. So we're gonna mixin file ICA underscore mixin, and metrics file is gonna be underscore metrics tsv. Cool. So now we're gonna load the mixin. So yeah, let's load the mixin matrix with pandas. So we're gonna do pandas read table, and we're gonna do. We are inside the TEDANA manual folder, so this is gonna be mixin file. And the shape should be time by components. We had 46 components. We don't have many components because I use the most aggressive PCA technique just to make sure we don't, spend too much time classifying components. But yeah. Now I'm gonna load the component table, metrics. Pandas read table, metrics file, and you can also type the shape. There you go. So the number of components, and then we have 22 different metrics. But more importantly, we're gonna extract columns of rejected, unaccepted components. So we're gonna do metrics df. And then we're going to look for the columns, so the rows that have rejected in the classification column. And it has to be rejected. And I'm missing something. Yeah. There you go. And we're going to do the same with the accepted. Okay. So now, just so you see rejected columns. Oh yeah, I forgot to extract the component. Yeah, this is what I wanted to see. I'm gonna do the same with the accepted columns component, and then accepted columns are this very few components. All right. So that means that we can keep going. We're gonna also load the confounds and select which ones we're gonna use. So in this case, we're gonna be using the movement, so the motion regressors and some CSF and white matter regressors. And then we're gonna be extracting the components of both rejected and accepted from the component matrix. So confounds, data frame will be pandas free table confounds file. Did I make a mistake on the name? Confounds task. I must have made that mistake here. Oh no, of course, yeah. Sorry, the confounds are not an output of TEDANA. They were an output of fMRI prep and are in the folder above. That's why we have to go back. I think you can do this with OPG. Yeah. So this would be the compounds. You see, you've got a bunch of other compounds like the global signal and stuff. So we're gonna select from these our compounds. There are gonna be some compounds, data frame, and we're gonna extract the trans X, trans Y, trans Z, both X, both Y, both Z, and then CSF and the white matter like that. And then we're gonna send it on by. There you go. Now we have a matrix with our compounds. And now we're gonna select the bad components and the good components using the columns we extracted before. So from our rejected components are gonna be from the mixing matrix. We're gonna get the rejected columns, and we're gonna make them pi. There you go. So here's our matrix of rejected components, and then the same with accepted components. Columns. Cool. So now we can start exploring the three different denoising methods. So we can do an aggressive denoising. So we can remove all noise correlated with fluctuations. So if you regress just the nuisance regressors, so the rejected components out of your data, you still retain the residuals for further analysis. And this would be considered aggressive. I know this is a big chunk of code, but it's not going to take too much to do it. Basically, what we're going to be doing is stack our rejected components and the confounds into a single matrix. And then we're going to use Nylern's nifty masker to denoise the data with those regressors, basically. So we want to import NumPy as MP, and then from nylern maskers, we're going to import nifty masker. And like I said, we're going to stack our rejected components with the confounds into a single matrix. So if we actually look at confounds shape from before, now we look at the regressors shape and see how we have components. The regressors are now both the rejected and the confounds. We're gonna create our masker with nifty masker, where the mask image will be mask image will be we'll have to go back to the folder above, and it will be the mask file. And we're gonna standardize confounds. We're gonna set that true, but we're not standardizing the data itself. We're not gonna apply any smoothing, so this has to be none. We're not gonna trend. Sorry, low pass and high pass values are also going to be none because we're not doing any band pass filtering. TR, we don't need this, so none. This is just for the filtering. And then report, we're going to add false as well. Standard. It's standardized. We'll do that right. Standardized, yeah. Okay, just yeah. So now we have our masking object. So we can denoise. So I'm gonna write it. Denoise the data by fitting and transforming the data using the regressors. And we're gonna do our denoised image in 2 dimensions. It's gonna be our fit transform of the masker to our data file. Now, this will be still 2-dimensional. So we've got time and voxels, and we want to transform back into 4D. And for that, we have to, well, we're gonna call it image 4D, and we have to do the inverse transform with a masker. Transform of the denoised image into. So the denoised image 4D now should be the number of voxels and the time points, and then we can save this image 4D to a file name. You could do it in the functional folder if you wanted to like keep working on keep using this denoised data in your analysis. So I just copied the name of the file I'm gonna use. So aggressive denoise bold. And so this would be the aggressive denoising. I forgot to add the RPG. Sorry about that. There you go. We could actually import this directory, the one above, and the aggressive denoise should be here. There you go. Cool. So that would be the aggressive way of denoising the data. Now we can also do a non-aggressive denoising. And so we would be removing fluctuations that are not correlated with the accepted components here. And so this is when you include both nuisance regressors and regressors of interest into your regression. But unfortunately, we cannot use we cannot do non-aggressive denoising using Nylern's masker object. So we're gonna have to do use NumPy for this. So here's the code if you wanna do it yourself. I'm gonna quickly go through it. So we need to import from Nylern's masking. We need to import apply mask and unmask. So we're first going to read the data with apply mask, and this is going to be the data file, and we have to go one off to get the mask file. G, there you go. So now we're going to feed the GLM to the accepted components. So for that, we're going to create our new regressors. Are also going to be stacked. And they're going to be the confounds, the rejected components, the accepted components, and then identity matrix here of the shape of its matrix. I think I need an extra one. No. Oh. There you go. Cool. So our betas are just going to be the solution to the list squares problem. Red source and the data, and our count is going to be none. And we're going to be taking all of this as the betas. Here you go. So we have our maps. And now we can use these betas, these maps to denoise the data from the bad components. So indexes of those are confounds in this case, and that's going to be the range of values, confounds matrix plus the number of components. Basically, how many components, how many rejected components and confounds we have, and these are going to be the indexes, and the data then is going to be the matrix multiplication of the confounds on the rejected components. Yes, and that's of those. Sorry. Comma and all of them. There you go. So the noise in this case would be that we just have to remove this confounds data from the data. We could save this into a new into file. So we're gonna unmask the noise data, and we're gonna save it in the functional folder. Sorry, we're gonna use the mask file first. Of course, we need the mask file. Unmask it, and now we can save it to file name OPG, the folder above, and I'm going to copy and paste it, the name of the file, to non-aggressive denoise. And again, we can do listener. And it should be here. There you go. It's the last one. Cool. And then finally, we could also orthogonalize the components with respect to the accepted components before we do the denoising. So if you want to ensure that the variance shared between the accepted and rejected components doesn't contaminate the denoise data, this would be the way to do it. So in this case, you can regress the rejected components out of the data in what we call pure evil components. And this would be the block of code. I don't know how I'm doing on time, but this is going to be real quick. Like, this is the last one, and I'm going to have 2 more slides, I believe, that are not code related. So is that okay, Hongko?
Yeah, that's okay. Go ahead.
Okay. So I'm going to quickly do this one. So with the orthogonalizing method, we are again going to use the nifty masker. So that's going to be much easier. So we're going to combine the confounds and the rejected well, we have actually done that just now, right? But just in case, I'm going to create a new variable where I stack the rejected components and the confounds. We're going to regress the good components out of the bad ones. It's like pure evil regressors. So we're going to solve the least squares problem. We're going to pass the accepted components, the bad time series, and our count will be none. There you go. Time series will be, we have to multiply our accepted components with us here, and to orthogonalize this bad time series, we're gonna just do the bad time series minus the so now we have orthogonalized the bad time series, and we just have to follow the same method we used before with the nifty masker. So we're gonna create a new masker. Mask image is gonna be above mask file. Standard confounds is gonna be true. Our dice is gonna be false. No smoothing. No. The trending false. Low. I'm not gonna do any low or high pass. The PR is gonna be none, and reports are blind reports. All right. But yeah, now that we have the masker, it's just gonna be just like we did before, the fit transform. The denoised to the image, we're gonna fit transform the data file that we already have some initially somewhere, and we're gonna pass confounds as the order of that time series. This is different to what we did before. Cool. So now we have denoise our data, and all we have to do is just transform it back to 4D. Inverse transform denoised image 2D, and now we save it. Define it. And again, I'm gonna put in the folder above and copy the name. I'm gonna call this disk. Oops, there's something. Organize aggressive denoise. There you go. And it should be somewhere here now. I don't know where. Anyway, so this would be how you orthogonalize your components. You can also use the TEDANA option that is built into TEDANA, but the problem with this option is that it does not consider the regressors. It only considers your components. So yeah, to recap, you can use TEDANA with use the -D and -E options, especially if you're like trying to like explore how TEDANA works and what it does to your data. Then remember that the automatic classification is not perfect. So as of today, I would recommend using Recap to explore your components and manually classify. And then you would rerun TEDANA with your manual classification. Then it's just a matter of deciding which one of the denoising techniques you want to use. You want to denoise with your confounds, or you just want to denoise with your components. Yeah, I already made a little teaser of this little teaser before. So as I was saying, we are about to merge a new decision tree to classify components. So when we do merge this, it will, like TEDANA will allow users to come up with their own recipes to classify components. And so this is some work that we started back at the end of 2019, if I'm not wrong. We're about to merge it, and what we think it's really cool, because then you create your own what we call nodes in a JSON file. You give it a name, you give it the parameters. If something happens, then you should accept or you should reject. And you can also share these recipes with colleagues, or even when you publish. So if you've done some denoising with TEDANA and you published your work, you could also share this recipe with the reviewers and the readers of your paper. So yeah, stay tuned for that. I hope we merge it before the end of the year. And yeah, so thank you for your attention, and do not hesitate to get in touch with me or any of the TEDANA developers for feedback, help, new ideas, whatever. Yeah, and if you have any questions, I'll be happy to answer them. Thank you.
Thanks, Eneko. That was great. That's a very dense tutorial session. I'm pretty sure people watch this on YouTube either live or later, and then particularly later, you can always pause the video and then follow the tutorial. So
yeah, and I didn't have time to like properly open the different denoising techniques, like the files themselves, and have a look at them. But I leave that to the viewers.
Yeah, great. Yeah, that's really good. And also feel free to distribute your recording to others that as a tutorial for you to give others to use, and so you don't have.
Yeah, I think we will add the YouTube video to our documentation somewhere.
Yeah, great.
Yeah, thank you.
Good. Let's just see if anyone has any question. Okay, so if not, let's move on to Camille. Hello, Camille.
Hey, can you hear me?
Yes, we can hear you.
Great.
So Camille will talk about MRI post-processing platforms and how they compare.
Okay, so I'm gonna try and share my screen, which was a bit difficult earlier, so hoping it will work better this time. Okay. So you can now see my screen. Can you see the slides full screen?
Yes.
Okay, great, thank you. So I want to start this presentation with a small disclaimer because this is not going to be a full hands-on session, and I'm sorry about it. I've had to dedicate more time to my family this winter than I had anticipated, and I hope many carers here will relate. But beyond people who are caring for other people, I think we all have personal lives, and sometimes they do impact on our work. So as I found myself saying more and more these days, we do what we can. And to finish on a brighter note, I'd like to share what the organizers, the nice words the organizers shared to me when I said I wasn't sure whether I'll be able to deliver the session. So they were first extremely supportive of me taking time off as I needed, which was great. And second, they said that, Sophie said that sometimes it's not only difficult to juggle with data, but also to juggle between professional and personal lives. And I think this is very true. That being said, I hope we still can have an enjoyable session. So today I'm going to talk about the post-processing side of things, focusing on different platforms and how they compare. So as I said, I'm going to focus more on different discussions, open questions, showing a little bit of code, and then I'd be happy to discuss afterwards about any detail you'd like to have more information on. So here on the left, you can see an overview, really high level of an MRI study. And so just to give a little bit of background about myself, I'm a computer scientist, so I'm more concerned with the second part of the data analysis, including data preparation and statistical analysis, and all of these will be covered in the post-processing aspect. I'm typically using brains to illustrate my slides because I'm a neuroscientist, but obviously this could apply to any type of MRI analysis. And over the year, the typical approach, or at least the historical approach to sharing results in MRI, but beyond in research, has been to writing papers and sharing these papers. But in the past couple of years, people have realized that this was often a bit limited because it was difficult to reproduce previous findings. And of course, when we worked in research, there are different times where we might want to reproduce an existing study. So starting from the paper, sometimes I want to build on the work of someone else. And the first step is just to reobtain the same results. And by doing so, just looking at the paper, I often end up with like many questions. So I've put a few here related to my field of study, which is task-based fMRI. So for instance, it might be unclear which particular release of the SPM software was used, or maybe details about the registration algorithm or how the brain mask was computed is not always included. And this means that it's a lot of work to restart from zero when we want to build on the results of an existing scientific paper. Another occasion, sometimes I've managed to reproduce, to do a reproduction of what was done in the paper, but what I get is different from what was published. And there we're really at a loss because we don't know why this is happening. Did I understand the method correctly? Maybe I didn't understand correctly and my re-implementation is just not matching what was done by the original authors. Or maybe it's because I'm using a different data set and that creates different results. Or maybe it's because I'm using a different computing platform and so on. And so when results cannot be reproduced, as I was saying, it's often very difficult to understand why this is happening. And throughout the year, there has been more and more emphasis on reproducible MRI with focus on different aspects. And that's what I would like to give a brief overview here of the different aspects of reproducibility that can be covered, finishing by the different post-processing platforms, which we'll be mostly interested in. So when we talk about having the ability to reproduce an MRI study, there are many aspects of our study that can change. So I've put three main classes here. So the first one is using the same data or a different data set. And this has been discussed a lot at the beginning of the reproducibility crisis, and I'll get into this. But we could also do the same analysis with a different method. And here method is very broad, can be different type of acquisitions, different type of data preparation. Maybe it's the same algorithm, but in different software and so on. And finally, there is another level that is about who is doing the reanalysis. Is it the same experimenter? Is this someone external? In which case, you also have to ensure that enough information has been transmitted between these two actors. And in fact, here I'm copying a table from the COVIDAS guidelines, which were produced by the OHVM community, focusing on what does it mean for to have reproducible neuroimaging. And here you can see on the left all the rows, so I'm not going to cover all of them, many different levels of generalization that we might want to tackle. And here we retrieve our big different aspects, including data sets. So we might want to look, if we go back, sorry, at, maybe you can see my mouse. So we might want to look at a different population, or maybe the same population, but with a different sample, and so on. We might have different methods in terms of acquisition, in terms of how the experimental design was built, or in terms of post-processing. And also we might have different people doing the replication. So there are many, many different levels, and all these different levels inform us differently on our analysis. And that's where I'm getting at in the following. So when we say we want to fix irreproducibility, we have to be specific about which type of irreproducibility we've been targeting. And so if we have irreproducible results with the same data, a number of approaches have been proposed, including sharing code, containerization, because this can solve the issue of having not enough details about what were the processings that were applied to the data. Again, here I'm taking the post-processing approach type of things. Now, if the results are irreproducible when I use the same post-processing, the same machine, and so on, but a different data set, these might be first an indication. Well, at least it was first looked at in the community as an issue of small power, small statistical power. And so I'm reusing this graph that was published in 2017, so a few years now, in Nature Neuroscience, that was showing the median sample size of task fMRI studies going from the mid-1990s to 2015. And we could see that this had been increasing, the sample size, so sample size typically being the number of participants. This had been increasing, but in 2015, we were still at about 30 participants. And this creates a statistical power that is low if we want to look at effect sizes that are particularly small. So here on the left, there is this example that comes from Genomics, in which a landmark paper that showed the association between a specific gene and the risk of depression was reproduced a few years later, but the reproduction failed with a larger sample. And the explanation here was probably that the first study was a false positive due to a sample size that was too small to study the problem at stake. And in neuroscience in general, the issue of low statistical power has been largely discussed and addressed in the community by increasing data sharing. So with the idea that we should move, I think we should, this is a reflection that has been going on in the field for quite some time, and we can see now that sample sizes are moving to becoming bigger so that we can answer a broader range of research questions. So this is one first explanation of why results might be irreproducible when I use a different data set. Another one is the lack of generalizability and equitability. And here in this example that is based on scientific work that was done by Joy Buola-Winnie, they were showing how commercial facial recognition systems basically had error rates were had lower performances when trying to recognize Black women compared to white men. And looking into the data that were used to train this algorithm, they basically had identified that the data set had much more white men, and basically the algorithm had been trained on this data was better for this class of the population. So this asked the question of the representativity of the data sets, and in a recent study by Lara Zabal and colleagues, this was also shown in the field of medical imaging. So here it was X-ray and lung opacity detections, and they showed how if the model was trained only on images that came from male and tested on female, then the algorithm was not as powerful as performance that if you had initially a diverse sample to train the data. So here this pointed out to the need to have more representative and diverse data sets. And here I'm insisting on the idea that we need diverse teams as well, because basically changing why the data was biased in the first place is often related to who is doing the research and who is leading the research. So those two aspects go hand in hand together. So the field, after realizing that there was an issue with reproducibility, has been reacting in the past few years. And we've seen an increase in open data, going initially to sharing data set at the end of one study. So studies typically with our 30 participants, to building consortium. So where researchers ahead of time would join efforts together, agree on an acquisition protocol, and then generate data in different centers and then pool the data together so that they would achieve larger sample sizes. And I think one of the pioneers here was the 1000 functional connectome project. And even more recently, we've seen funders realizing that this is an important issue and specifically dedicated money to fund data sets that are resources for the community. So those include the Human Connectome Project and the UK Biomet. But this was a first aspect of irreproducibility. But beyond that, we can ask ourselves, what can we do when we see results that are irreproducible when using different post-processing methods? And so here I'm going to give a bit more details about what might vary in this post-processing. So I'm going to use method and pipelines indifferently, and there was platforms in the title. So when we describe a pipeline here on the left, going from our raw data coming out of the MR acquisition system, we have a phase of data preparation, which is basically making sure that we get a measure that is the measurement we are interested in. So this can include denoising, registration, and so on. We get some derived data, and then we can run a statistical analysis on it or machine learning algorithm to get our final results. But in practice, we don't have these two high-level steps, but it's more something like this. And in fact, it's even worse. It's more like a tree with branches going in different directions. And each circle here is a different processing. And in fact, for each processing, I have a number of choices that I, as a practitioner, have to make. Often there are multiple algorithms that are available for a particular step. Even if I use the same algorithm, it might be available in different software packages with slightly different implementation. even with the same software package, there are typically multiple versions, and different version will have, again, different implementation of different steps. And even with the same software version, there are typically a range of parameters that I can choose from. So basically, I don't have a single post-processing pipeline that I can use to answer my problem, but I typically have a family of acceptable pipelines. So here on the left, we have a canonical example, and then we have in second a variation with different parameters. The third one is another variation where we change two algorithms. The fourth one is the same, but with the software version that was just before, and the last one is the same with a different software. And as you can see, using a different software can also have an impact on the type of algorithm that are available. And here for step 2 and 4, we also had to change the algorithm. Those are just 5 examples, but if we try and vary all these different aspects, we can end up with a family of acceptable pipelines that is extremely, extremely, extremely large. And for quite some time, we as a field, we're not, I would say, so much worried about this level of variability. But recently there was this study. So a number of papers had been looking into what we call analytical variability. So the idea that different pipelines can lead to different results. But this particular study that I'm going to present here, which is called, known as NARPS, but was published in 2020 in Nature by Botvinnik-Nezer and colleagues. Basically, this study showed in the wild that this could happen. So basically, it worked as follows. There was one data set that was carefully acquired with a rather large sample size of over 100 subjects. And there were 9 yes or no research questions. So yes or no research questions, I've put an example here. Is there parametric effect of gain, positive effect in ventromedial PFC for the equivalence equal indifference group? So you have a very specific question about an effect that you want to test in a specific region of the brain, and the answer has to be yes or no, and there was in addition a confidence level. And then they recruited different teams, and in the end, they managed to have 70 different teams. So I think the teams were 1, 2, or 3 people maximum. And these teams were asked to analyze the same data set to answer the same 9 yes or no research questions. And here's what happened. So first, each single team chose a different processing pipeline. So these show the variability of the post-processing that are chosen in the wild. And then we have this nice plot that summarizes the results of the different teams. So here at the bottom, you have the different research questions that were asked. And then at the top here, when we have, so we're going to look only at the red values here. The red values that are at the top corresponds to a hypothesis. So here, hypothesis 5, where we have a significant finding, and the teams, most teams are agreeing. So I've put a threshold here at 80%. So 80% of the teams agree that there is a significant finding. At the bottom, the same, but in the opposite direction, most team agrees that there is a non-significant finding. And this is the case for 3 of the 9 hypotheses. And then in the middle, we have contradictory results. Basically, the teams disagree to the yes or no question of whether or not there is a significant finding in the region of interest for the effect that is tested. And of course, this led to many questions in the field and beyond. And in post-processing pipelines, as I've shown earlier, there are different levels that can vary: the parameters, the software version, the operating system. And there are a number of studies that targeted specifically these aspects to look at whether or not they had an impact on the final results. So I've put a few references here. And in the following, I'm going to focus on post-processing software packages. So using the different software packages, but trying to have pipelines that are as close as possible, with 2 publications from that, so that we did in a collaboration with Alex Boring and Tom Nichols from the University of Oxford. So the idea here was to reproduce 3 published functional MRI studies. So I put the handle here. These are publicly available on OpenEuro, using 3 different software packages. So it was the same data, the same pipeline, but except that we created a variant for each different software package. And AFNI, FSL, and SPM being 3 of the most widely used software packages for task-based fMRI. And so here's what happened. So you can see on the left the final results, so the threshold maps. And here at the bottom, the last line corresponds to what was published in the scientific papers. And each column is a data set. So here you can see, for instance, for DS01, the first data set, here with the black background is the results that were obtained in the paper. And here is the reproduction with XPM, with FSR, and with AFNI. So you can see that for this example, the closest here to the original paper is the FSL pipeline, which is a good thing because that was the pipeline that was the software that was initially used in that paper. So you can see, but you can see non-negligible variability across software packages. For instance, here we have this cluster that completely disappears and so on. And we also made comparisons on the statistic maps themselves. And in the following, I'm going to try and have a look at the code. So hopefully, so here following this link, I get to this GitHub repo. Can someone confirm that you can see my GitHub repo okay?
Yes, we can see our...
Okay, thank you so much. So I had so many problems sharing screen. I just want to double check everything. So, so here we are. We have this GitHub repo, which is the companion for the research paper. So here, I'm just going to give an overview of how it's organized and where we can find the different code, and then we can have a look at it together. So first, we have a README where we try to include all the information, well, at least enough information to guide someone who would come from the publication. So we can open the publication here. So we start with how to cite this repository. So we suggest just to cite the paper directly. And then we have 2 big sections. So here you can see in the table of content, how to reproduce the figures and how to rerun the full analysis. And so if we get here, just going to quickly browse through so that we can see the figures. Okay, so here's figure 1. So that's the same as the one I was showing earlier. And so we can go here and to reproduce, to reproduce figure 1. So first we would have to install the dependencies. And then there is a Jupyter notebook that is located in figure and starts with the identifier of the data set. So if I go back up, I'm going to open the figure folder. And then DS01, let's go back, Jupyter notebook. Here we are. So I'm going to open this one. So it's a big. So basically what this notebook is doing is that first it's going to go on your Vault and download the data where all the derived, basically the statistical maps and the thresholded maps have been uploaded. So basically to reproduce the figures, a user would not necessarily have to reproduce all the reanalysis, but we have an entry point here that is the results we obtain, and then we can explore these. So this first step is really downloading the data, making sure we have everything in the form we need. And then if we want to, let's say, reproduce figure 1, we go here and we found the cell that starts with this. So here it is. And here we can retrieve, this is our AFNI view. So going back here. And then we have our FSL view and our SPM view, and the last view came from the original paper. And here we go we can do the same thing with the second figure. So looking here in the paper, so that was the second figure was about the threshold heat maps. And so here I have an indication of where I will find this in the notebook. So here it is. And again, here, these three are the unthreshold heat map that we would see. And then, so that was to reproduce the figures. And then at the bottom, for someone who'd be interested in rerunning the full analysis or reprocessing the data, there's first instruction about how to download the raw data and then how to redo the analysis. Of course, a number of parameters have to be reset, in particular in terms of paths to the raw data once it's downloaded, paths to where the results are going to be stored, and then there are a number of scripts that let us run the analysis. The way these scripts work, maybe I can get a little bit into this. Process. Just going to retrieve where it is. So it should be into. No, sorry, these are the results, not the scripts. So the scripts are here. And then process, SPM. And so the way it works is that it's going to specify the condition, create the onset files, and so on. And then we have template files. And this, if you are an SPM user, you will recognize this. So basically, all the code in that repository is based on the idea that we have template for the MATLAB batch for SPM or for the FSF files for FSL, and for, I guess, AFNI proc for AFNI. And then we have placeholders to replace with the actual data. And then the script we were looking at earlier, the script here, when it runs the run level analysis, is going to fill in the right data for that particular subject and then apply the MATLAB batch for SPM, the FSF for FSL, or the AFNI proc for AFNI, and run the full analysis. And once you've done that, you can reproduce the figures. So out of this study, I'm going to go back to my slides. There were a number of conclusions. So the first one was that we actually could observe differences across software packages. And I insist here to say that the pipelines were aligned as much as possible. And not only using the default of the software, because sometimes they have default that by themselves will create expected differences in the results. So typical example here is, for example, the output voxel size. If you look at maps with different resolutions, of course, they will be different. So we tried to align as much as we could, but at some point, you basically don't have access to deep down differences that are implemented in the software. The differences were more pronounced with the threshold heat maps, and this was expected. Basically, the thresholding step is very sensitive to small variations. And the immediate questions when we had done this work and with many other work looking at differences across different pipelines is, why is this happening? So we've seen that post-processing pipelines can vary based on many different aspects. We've talked software, parameters, different algorithms, and how, can we pinpoint what in all these differences is creating the most variations? And that's what we tried to do in a follow-up paper. So here, still with Alex and Tom, you can see, so we've made variations of the pipeline. So here, and these are represented with the small graphs. So here on the left, we start with the full AFNI. 1A is a full AFNI pipeline. So we use AFNI for the pre-processing. We used AFNI for first signal. We used AFNI's first signal model, so basically the design matrix. We used AFNI's drift model, AFNI's noise model, and we used AFNI for the second level inference, modeling and inference. And then the two here are parametric versus non-parametric, but we can look at the blue only for now. So we go from full AFNI to here on the left, 7F, full FSL, so still all these steps in FSL. And in between, we do different variations. So the first main thing we try to align is to use the same preprocessing. So here 2AF is using fMRI prep for preprocessing, and then the rest is done with AFNI. And then we make another variation where preprocessing with fMRI prep, signal, drift, and noise, first level modeling with AFNI, and then second level modeling with FSL, and so on. And this is a way to try and vary just a single step at a time. And those differences across software packages were extracted from expert knowledge. So thinking about, once you've removed the preprocessing, which is a big chunk, thinking about the statistical analysis, what were the differences that were encoded in different software? And we know the way design matrices are done are different. For instance, there is a different HRF between the 3 software packages. The way drifts are handled are different. Noise modeling, I could give more details about that, but it's different as well, and so on. And so we try to say, okay, these are, we think, the main differences across software, and just vary these and see which one had the stronger impact. So then these were the different variations, and then we could create figures like this one, where we're going to have the results, so going from full AFNI to full FSL with different variations. And here we've cut to find the point where we had the biggest difference. So I'm not going to go through, I can open the code, but it's very similar to what we had earlier. So we find again the same structure with reproducing the figures and the tables, and then the full analysis. And so, can you see my full screen now? I'm hoping. Can you see back my slides? Because I changed windows and I'm not sure I can.
Yes, full screen. Sorry, I was muted.
Okay, thank you. That's all right. So here, out of this study, again, the goal was to find what were the main sources of variations. And the thing that was a bit that makes it difficult is that what we found is that the main source of variation was different for each data set we studied. So for DSO1, which is presented here, the main difference was the first level signal model. And you can see here, so that's the transition between this one and this one. You can see the big yellow cluster just disappearing. And this is a change from AFNI first level signal model to FSL first level signal model. If I remember correctly, this is a study where there was orthogonalization, and this might be an explanation of why there is difference with the first level, like more differences impacted by the design matrix. DS109, it was the first level noise model that made the strongest differences, and DS120 was the group level model and inference. And here again, we had a different setup with an F-test. So it looks like the different particularities of different studies might impact which variation of pipeline has the strongest impact. So this leaves us with many open questions. And so if we want to go further with understanding this analytical variability, with understanding the fact that when I change my analysis pipeline, I get different results, what are different ways we can look at this problem? And before I go any further, I think there are 2 main reasons why we might be interested in better understanding what's going on in here. The first one is that if we get different results by using different pipelines, we can think that there is an impact on the reliability of existing findings. So if we think about the NARV study, does it make sense that 70 teams of experts disagree when they start with the same data set and have a very well-defined research question to answer? But it also impacts the reusability of derived data set. Because basically, if the nature of the data we're getting from one pipeline on one post-processing software to another is different, that means that tomorrow I won't be able to just pull together results from SPM, FSL with different parameters, and so on. So I think there is, and in a world where we're trying to increase sample sizes and use, like, make the best use we can of the data we have, this is an important problem that we should look into. But this is a difficult problem, and I've tried to touch upon this throughout the presentation, but I'll just summarize here with a small chart. So when we get different results from different pipelines, we can explain it in many different manners. Some people have looked at numerical uncertainty. So the fact that you're going to feed into your pipeline a data set that is slightly modified with small level of noise, and then you check at the end whether the answer you're getting out of the pipeline is still consistent with the data that was not modified. And when this happens, I mean, when we get different results at the end, it tells us something about our pipelines. It's basically unwanted variability that we would like to get rid of, because it's not normal that if I had a very small little level of noise to my data set, I get a different answer in there. There is also unwanted variability that is a little bit hidden in that there are different implementations. So sometimes we talk about algorithms and we don't have the full details. I mean, we can't, like when we describe our research in paper, we only have so many words in the method section. But sometimes there are hidden implementation details that actually matter and can make our results different. Then there is what I've called data-induced variability. Sometimes, because, for instance, I don't have enough data points, using one pipeline or another is going to provide very unreliable results just because the input data set was not enough to answer the question we're trying to answer. And sometimes the data set we have might violate the assumptions of our methodologies. And that's very difficult with a pipeline because each step has its own assumptions, and we have a pile of assumptions in the end. And finally, and I think this is why we are all looking at different pipelines, there is the variability of interest. There is the variability that is going to inform us on our research question. For instance, let's take an example. If adding age as a covariate in my design matrix give me a different result, then it tells me something about my problem. It tells me that my input data had a dependence on age that is that has to be modeled for the results to be meaningful, for instance. So there are all these different aspects going all the way from a variability that we would really like to get rid of to the core variability of interest that is the core of our research. So on our way to better understand what's going on, I just wanted to finish by sharing different aspects that we can start today focusing on. So the first one is to share a variety of research artifacts. And in particular code along with papers. So I think you're probably all aware here that sharing just a research paper is the minimal research artifact. And there is so much more we can learn if we can share, if the code is shared, or even maybe the derived data set in the middle, or maybe the results data set. We don't have to share everything at once. So maybe for one study, we start sharing just the code, and the following one, we share a bit of code and a bit of data. But in the long run, this will help understanding better what's going on. Storing and sharing provenance. So I didn't describe provenance in here, but provenance is a complete machine-readable description of what happened to the data. And in my case, I'm mostly interested in these post-processing approaches. So if we could share with our results in a file a description of what happened in the data, and some software already store this kind of information, that's the case in AFNI with the history in the brick files. In SPM, you can share the MATLAB batch, and in FSL, the FSF files, which give us a trace of what was done. And then again, in terms of how we can limit that space and provide best practices as to which pipelines might be better than others, I think there's still a need to benchmark different methods, even though I truly believe this is extremely difficult in our field, because typically often we don't have any ground truth that we can use to find out which one is the best method. So with this, I'll thank you so much for listening to me today, and I'm happy to take any questions if we have time.
Awesome. Thanks, Camille, for the nice presentation. Yeah, I was actually going to ask the question but you have actually answered. So how are you going to benchmark different pipelines? But you said there's pretty much no ground truth, so it's going to be difficult. Can you comment on that?
Yeah, so there is some work trying. So I'm thinking about the work of Daflon and colleagues. So trying to use prediction of age and trying to find the pipeline that best predicts age, or you can use other phenotypes. So I know colleagues in Paris, Baptiste Couviduchen, who is looking into that as well, like trying to see which pipeline has more information to predict your phenotype. So that's not perfect, because you need to have a phenotype that is relevant to whatever you do afterwards. Like, I'm not sure, like, is the pipeline that predicts age the best, the one that we want to use for everything? I don't know about that. So I think you probably need a range of phenotype that you try to predict. But it's really hard, and that's why I'm putting it out there. I'd be really glad to see like people working on it more.
I agree. I think even if you have a pipeline, for example, correlate with the age prediction the most, but does that mean that pipeline is the most accurate? It's just supposed to explain like 100% of the age prediction, right? So in that case, that can be problematic as well to benchmark your methods.
Yeah, I think the idea here is that you can extract information from the brain that can help you predict age. But yeah, I think it's imperfect, but we need some ways. So there is work in like software testing in other fields such as bioinformatics, and some approach when you don't have a ground truth is just like have two concurrent approach and see if they agree or disagree. And then you don't know which one is correct, but at least you know there is something odd. And that's a bit what like the numerical instability papers are doing, basically with different data. But if you get different results by slightly modifying your data, then it tells you something about your pipeline.
Right. Yeah, I know in deep learning, we some people do this as well. Like you perturb your data with some noise and see how your pipeline or your algorithm is, how stable it is with the perturbation. So that's something very smart, I think. Let's see. I think Mo has a question for you. Okay, I think it's that's the same question. So what would be the solution then? Writing analysis code without using packages?
Oh well, no, please. So the issue is if you start writing analysis code without using packages, I think we're going to explode the variability because each of us is going to have a different implementation. So I truly believe that we should have like community tools. That's also useful because then we have more set of eyes to like find bugs and more people are using it, and that's probably easier for like good practices in software engineering. I know you had a session about this earlier today morning here. So I think we should rely on the software packages, the one that exist, if they answer our problems, but we should understand better what are the relationship between one another. Sometimes there are a lot of assumptions and sometimes we are aware of them, but sometimes we don't.
Yeah, sounds good. Yeah. So I see you were trying to replicate the the paper that they use FSL for as the pipeline. So what's the reason you couldn't like 100% replicate their results?
So first, it's really hard to find which percent, like how good the replication are, because all we had was the figure in the paper, right? So it's like you have one slice and you can see whether like it looks really like it matches or not, but you never know if it's perfect. I guess what you're saying is that it did not look perfect. There is work that shows that even different operating system can create differences. So I think small variations, probably the version of the software as well. I think we used the latest version of FSL because that was convenient. But again, this includes like changes compared to when the paper was first published. So yeah. So I think we have to like reach a level of what we think is in agreement or not.
Sounds good. All right. Thanks very much, Camille. That was a great presentation, and hopefully the FMI community and you guys can think of a solution and then to improve the reproducibility and accuracy.
Well, thank you so much. It was really nice to see what's going on in here. So I hope to see more in the future.
Sounds good. All right. I think we will just end our session here. And thanks everyone for attending. We'll see you in the next session.